But Michaelis, Menten, Kinetics. So first of all, since we're going to deal with allosteric enzymes later, this implies that we're not dealing with allosteric enzymes here. We're dealing with non-allosteric enzymes. What does that mean? To be a non-allosteric enzyme.
One substrate binding the enzyme.
Yeah.
There's no secondary binder.
Awesome. One substrate, one enzyme, and there's nothing binding to any other sites that activates or inhibits or anything like that in a normal sense. We'll talk about inhibition a little bit, but no kind of standard, so feedback inhibition or anything like that going on here. No allosteric effectors, we say. So in this case, Michaelis, Menten, Kinetics. There's a huge long derivation, right? So, and your book goes through the whole thing. It's lovely. We're not going there. We're just going to assume they derived it correctly, and we're going to deal with how to use it. Because deriving it is not so important for this class. If you were taking 461 and 462, deriving it might actually be important, because you might get a question on your test that just said derive it, and that would just suck so bad. But remind me, are you in 461 and 462? No. Oh, great. So we're not going to have to derive it. Life is good. So let's just put your Michaelis-Menten equation on there and some basic assumptions. So first, we assume that first thing that happens is enzyme and substrate bind together. So we'll use E for enzyme, S for substrate, and when they're bound together, what do we call this thing? Yeah, your ES complex or enzyme substrate complex. So, and then we assume that the enzyme substrate complex converts your substrate to product, and it kicks your enzyme, free enzyme, back out. So it lets the product go, if you will, once it catalyzes the reaction. So the enzyme substrate binding is reversible. We call the forward rate constant here K1, the reverse rate constant K minus 1. So, but we assume, and this is an assumption, it's not actually technically always true or even necessarily ever true, but we assume this second step is irreversible, that it does not go backwards. Here's the deal though, enzymes actually can catalyze reactions oftentimes in both directions. It's just which way do I need to go to get to equilibrium. So, but the assumption we are going to make here is that the second step, actually forming product, is irreversible. Cool? So, and if you go through and make some steady state approximations, with the steady state approximation just says that the amount of this that's in my solution is constant. So which means that the only way I make it, E plus S going to ES, the rate that that happens is equal to the rates in which it gets consumed, in which it's formed products, and which it dissociates back to free enzyme and substrate. Those rates are all equal. The rate at which it's formed and the rate at which it's used up are matched. That way its overall concentration is not changing. And derived from that steady state theory or steady state approximation is all the rest of it. But that's all they were saying. And then they just do a lot of algebra and, total enzyme equals, free enzyme and bound enzyme. And we make a lot of assumptions going down the line and a lot of substitutions, which we don't have to do. But we do need the result. So in your result is that V equals V max times your substrate concentration over Km plus S. So a couple things. Had we actually derived this, we'd know a few more things than we currently know. We'd know what Vmax actually was, and we'd know what Km actually was mathematically as well. And what they are, for you guys, is really not actually quite as important as what they represent. So let's go there. So first off, your Vmax. So we'll talk about what he represents, and obviously what is Vmax? Maximum velocity, and the velocity is the same thing as rate in this case, but maximum rate or velocity at which your enzyme can be produced. So I want you to think about these enzymes as factories. Factories. Enzymes are factories. And this particular company has these factories all over the country. All over the country. So, and the ones that are in the big cities, they're just moving as fast as they possibly can. But the ones that are in the smaller locations, they're not quite so busy. They just don't have as much to do. And so in that case, the busy ones, they always look like this. They always have substrate to process into product. But the ones that aren't so busy, sometimes they look like this, sometimes they have stuff to do, sometimes they don't have anything to do. They don't have any substrate bound, i.e. anything to do. And that's the way it works. Now notice, if I give this company across the country more and more stuff to do, if I give them substrate, well, eventually they're just going to send that substrate to all their locations and get all their factories operating at maximum capacity. And at that point, all their enzyme Nobody's going to have any lag time. They're all going to be busy. They're all going to be tied up and have as much substrate as they can handle. And so when all the enzyme is tied up in this complex right here across the entire country, that's maximum capacity. And the Vmax would equal K2, the rate constant here, times this concentration, ES. That's the rate of the second step. But in this case, since all the enzyme looks like this really comes out to K2 times the total enzyme concentration. If all of it looks like ES, technically ES should show up here, but at maximum capacity when we're saturated, they say, all of it looks like this. And so the total enzyme would be the same as ES complex in that case. But this is your Vmax. So when we look at all these different graphs and stuff like that, we are looking at a single set amount of enzyme. That's what we're looking at, a single set amount of enzyme. We're never changing it for that one graph. Notice what would happen if I doubled my enzyme concentration, though, my total enzyme concentration? Vmax would also double. Cool, so keep in mind there is that relationship, but on any one single graph, that's not what we're looking at. For any one single Michaelis-Menten graph or Lineweaver-Burke plot, we're looking at a single set constant enzyme concentration for that solution, or that set of solutions, really. Okay, Km. Now, it turns out if we actually looked at the derivation of Km, Km would be related to the constants K1, K minus 1, and K2. It would be related to all of them. Well, it turns out we just kind of, ignore the fact that it's related to K2, and we really just look at the relationship between K1 and K minus 1. Notice K1 is involved with substrate binding. K minus 1 is involved with substrate complex dissociation back into free enzyme and substrate. And so in this case, Km, ignoring the K2 part of it anyways, which there's some assumptions why we do, but Km is related then to substrate binding. So it's kind of an equilibrium constant involved with substrate, well, really binding, I say, but dissociation. And so the way it works is the higher your Km value, turns out it's inversely related to binding. So that would actually mean lower affinity. So a higher Km means lower affinity. A lower Km for a certain enzyme would actually mean a higher affinity. You need to know that that's an inverse relationship between Km and the affinity for binding substrate. Cool?
Km's a concentration, right?
And Km has units of concentration. It's a very specific concentration of substrate, which we're going to see on the next graph. So if we look at this here, so if we make a plot of velocity versus substrate concentration, what we usually see is that the graph goes up pretty linearly with substrate concentration, at least for a while. And being that it goes up linearly, so, well, if you kind of looked at a rate law, so assuming this is linearly, you double substrate, doubles velocity, triple substrate, triple velocity, all along this line. What order would that correspond to in a rate law? That correspond to first order. And so in this part of our curve, it typically at low substrate concentrations, it behaves like a first order reactant. So however, that once you start hitting saturated, once you start getting all the factories out, all the factories across the country, operating at maximum capacity, totally saturated, they say, all of a sudden now, up here, so we kind of approach a horizontal asymptote. We never quite reach it, but we're always approaching it. And so all of a sudden, there's a maximum velocity we can reach. And notice out here, if I increase the amount of substrate, what happens to the rate? Hardly anything. The rate barely changes at all out there. And so you can add more and more substrate, but the rate doesn't change. And so out in this flat portion, this horizontal portion of the curve, as you approach what we'll find out is Vmax, what order are we talking about there? Zero order, because anything to the 0 power is 1, and it kind of falls out, and rate just equals k at that point. And so that's why over here it's first order kinetics, but over here it's more appropriately to look at it as being 0 order kinetics. So it's not just a simple rate law in this case.
Is Km an association or dissociation constant?
It's a dissociation constant, it turns out. So we associate it with affinity, but it's actually the exact reverse. That's why it's a higher Km means a lower affinity.
So, okay.
Cool, cool. All right, so the asymptote here, the horizontal asymptote we approach is Vmax. So, and then you have that special point, right? So if Vmax, say, came out to some arbitrary value like 10, then where would I go on this velocity line to find the next important useful piece of information? I'd go to 5, and halfway up to Vmax, that velocity, go to your curve, and where that crosses the substrate line, that is where your substrate value would equal the Km value. And so from a plot like this, we can very quickly, kind of at least get approximate values for both our Vmax and our Km. But notice they're really just approximate, because, what are the odds that on the plots, on the, all the different points you plotted, that you exactly hit that exact halfway point? Maybe you did, maybe you didn't. They're kind of approximate. If I want to do more than just simply approximate them from a graph like this, what do? We'll go to the Line-Weaver-Burke. We're going to do that in a sec. So one thing to note, if you look at this equation, so if you notice, let's say I told you that we're at the point where the substrate concentration equaled Km. Substrate equals Km. Well, look at what this equation becomes at that point. So V equals Vmax, and what's substrate equal to right now? Km. All over Km. And again, what's substrate equal to? Km. What's Km plus Km? 2Km. What's Km over 2Km? Just 1/2, actually. The Km's cancel. And that's why, at the point where your substrate concentration is equal to Km, your V comes out to equal 1/2 Vmax. That's where it comes from. It just falls right out of the Michaelis-Menten equation. Cool? Sweet. So let's talk about Line-Weaver-Burke. How many of you guys are loving Line-Weaver-Burke? One person, sweet. I appreciate your enthusiasm. Line-Weaver-Burke is not as bad as it looks. So what's the slope-intercept equation of a line? Y equals mx plus b. So what we're going to do on the Line-Weaver-Burke plot here, instead of plotting v versus s, we call it sometimes also the double reciprocal plot. And so 1 over v versus 1 over s is what we're going to plot. And so in this case, I'm not going to use the Michaelis-Menten equation as it stands. I don't need v, I need 1 over v. And so what we're going to do is we're going to invert both sides of this equation to preserve the equality, and then check out how that matches up to the equation of a line. Cool. All I've done so far is just invert both sides. All I've done. And my goal is to set this up so it matches y equals mx plus b, where x lines up with my x-axis 1 over s, and y lines up with my y-axis 1 over v. So if you recall, property of, a fraction here, if you have 2 terms in the numerator, you can actually spread that out into 2 separate terms. That's what I'm going to do here. 1 over v equals km over Vmax times s plus s over Vmax times s. Anything going to cancel out of this? Substrate cancels. And I'm just going to write this just a little bit different from here. So here we're going to have 1 over v equals km over Vmax times 1 over s. Notice this km over Vmax times 1 over s is the same exact thing as this term we had up here. And then this last term, 1 over Vmax. And my whole point in doing this is that now y equals mx plus b. So, and there's what I plotted on the y-axis and the x-axis. And so in this case, what is the slope of this graph going to be equal to? Oh, my bad. I said slope and pointed at y-intercept. What is the y-intercept going to be equal to? 1 over Vmax. What's the slope going to be equal to? Km over Vmax. And so from the slope of this graph and the y-intercept of this graph, you can get both Km and Vmax, provided you've already calculated those. Cool? So if we kind of look at this graph now, plotting 1 over v versus 1 over s, it indeed gives us a straight line. So in a couple of noteworthy things, this point right here is your y-intercept, and that's the point that equals 1 over Vmax. Your slope of this graph is equal to Km over Vmax. Now, can you ever have a negative substrate concentration? No, you can't. And so the rest of this graph that I'm going to draw in is imaginary. We're just kind of extrapolating, well, what if I did have a negative substrate concentration? What if I lived in some other universe where that was possible? I can have less than 0. Well, it's not. So, but actually, if you rearrange this equation and solve for the solve for the x-intercept, that would be where you set the y equal to 0 and solve for x. That gets you the x-intercept. What you'll find is that x-intercept right there equals negative 1 over Km. Cool, so if you have all these points plotted for you, notice you're not going to have to plot these points yourself on a test. That just takes forever. But if you have all these points already plotted for you, well, if they give you the value of the y-intercept, sweet. You can just use it to get Vmax. If they get you the value of the x-intercept, and that's probably not so likely, but if they do, great. You just set it equal to 1 over Km and solve for Km. You get Km from that. So, and you got both Km and Vmax at that point. Much more likely is they're just going to give you the equation of the line in all likelihood on this test. So, and if they do that, if they told you that the equation of this line came out to, y equals 50x plus 10. I don't know, I'm making up numbers. These have arbitrary units. Just making up a random equation, just for demonstration purposes to see how this works. So first thing I'm probably going to get, I look at that, I'm getting Vmax. So, because in this case, this is my y-intercept. So in a minute, I'm going to use my slope to get Km as well. So in this case, what's Vmax? 1 over 10. So if 1 over Vmax equals 10, then Vmax equals 1 over 10. Simple as that. So again, in this case, my y-intercept equals 1 over Vmax. And so in this case, which equals 10, if you invert both sides, you get Vmax. And so now we've got Vmax. Okay, now we need Km. So, and if you look here, what's Vmax? Well, we just got it. It's 1 over 10. You can plug that in right there and get Km. So in this case, what was the slope on this graph based on the equation of the line? 50. And so you just say, in this case, slope times Vmax equals Km if you rearrange it a little bit. So slope times Vmax equals Km. And so in this case, the slope was 50. Vmax was 1/10. And there's your Km, which comes out to a grand total of 5 again in some arbitrary units. Sorry, I should raise this board just a little bit here. So one thing to note, I actually do it a lot faster than that. When I get a graph, first thing I do is sweet, Vmax is 1 over that. And then I say that Km is that over that. Slope over intercept is what it ultimately works out to. And so I can very quickly be like, Vmax is 1/10, Km is 50 over 10, that's 5. Done. It's a 3-second problem. It's beautiful. And they're probably going to give you numbers that you can at least approximate in your head. Did they tell you to bring a calculator to this test? Yeah. Oh, they did. Okay, well, maybe they're not going to give you numbers in your head then. Never mind. So, but it's something you can do very quickly, and it's something you might want to get fairly quick at. Sweet. Questions on your basic Michaelis plot and your basic Lineweaver-Burke plot?
Can you talk about setting the x
Cool. If you set the x-intercept to 0, that's where you find out that the x-intercept equals negative 1 over km. But notice, how do you get the y-intercept, first of all? Well, the y-intercept is where the x value is 0. So when y equals mx plus b, if you plug in a 0 right here, you just get y equals b, and that's why it's the y-intercept. Notice if you want the x-intercept is where the y value is 0. So you plug in 0 right here and set 0 equal to mx plus b. Bring b over, divide by m, and that way you get your x-intercept. At this point, suffice to say, I would probably just remember that it's equal to negative 1 over km. Did I need it in this case? No, I got everything I needed, here from the slope and the y-intercept, and that's what you're more likely to see. Notice, if they were nice enough to give you this graph and plot that point and that point, great. Even if they didn't give you the slope in that case, if they just plotted both of those points, you could totally still get both your km and your Vmax.